Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Well, thank you. As always, it's a pleasure to be here. And see by the title of the talk that it's going to be a sort of hectic talk that concocts a lot of different things together. So I guess my main goal today is to convince you that the different terms in the title fit together. So let's start from the last one, Occam's Razor. Oh, let's start from the talk outline. So first quarter of the talk, I'm going to sort of try to explain the connection between the different parts of the title, and there won't be much concrete mathematics in this. Then we'll move on to some concrete examples. These will be examples of the principles I'll be talking about, and they'll also turn out to be, most of them will turn out to be lemmas that I'll use in the final part of the talk. So the final part of the talk is a theorem and proof of that theorem, and hopefully the proof will use most of what we'll see in the second part. Okay, so back to Occam's Razor. Occam's Razor, so William of Occam said, pluralitas non est ponendra sine necessitate, which, if any of you know Latin, means plurality should not be posited without necessity. And if you want it stated in a more modern English, so we can go to the 40s or 50s, Einstein said, everything should be made as simple as possible, but not simpler. And in modern pop culture, this is known as the KISS principle. Keep it simple, stupid. So usually when we refer to Occam's Razor in the context of science, it means that there's some phenomenon that we want to explain, and there's several possible explanations. And so it's kind of rule of thumb. Usually the simplest explanation is the correct one. And so this can be used in philosophy, or it can be used in exact sciences like biology or geology. But it turns out that somehow it also appears a bit in mathematics. Of course, only as a rule of thumb. You have some mathematical object, and you ask, does it have a certain property? And you can think of very simple necessary conditions for that property to hold. And then when you study it a bit, you discover that those necessary conditions are indeed sufficient. So, did I say that in the direction I meant? Yeah, so, and then if you show that, that's considered an elegant theorem. It's considered an elegant state of affairs. And we'll see today that a lot of the theorems we'll see are such that the simplest possible explanation is the strongest possible explanation. And somehow, the main theorem I want to talk about today is one of those theorems that you see it's so simple it's almost too good to be true. And then when I was preparing the proof, I saw that most of the lemmas are also of the same flavor, and I found it sort of striking. And that's when I thought of putting the razor in the title of the talk. And I had this feeling that, look, we're discovering how elegant and simple and beautiful mathematics is. But then I realized it's sort of an illusion, because it's not true that most mathematical theorems are so simple. In fact, most mathematical theorems are too complicated to state. And I can prove that to you, because there are only countable number of statements we can make. And of course, there's an uncountable number of mathematical truths. And even though among those that we can state, most of them are much too complex for the simple human mind to understand. And among those that we can understand, most of them we can't prove. So among those that we can state and we can understand and we can prove, that's already a very thick filter that only lets more elegant statements come through. And OK, so now that was what Occam's Razor has to do with this talk. Let's go back to the first term in the title of the talk. So what is extremal set theory? It has nothing to do with classical set theory. You're given a family of sets. Usually this is combinatorics. There are finite sets and finite family. And you're given some information about their combinatorial structure, about their intersections. For example, every two sets intersect, or every two sets have intersection of a given size greater than something, or some algebraic condition on the intersections. And then what can you say about the family? Either about its structure or its maximal size. And usually, how do you approach these problems? Usually, either use elementary combinatorics, straightforward combinatorial techniques like shifting or something like that. Or sometimes you can use linear algebra, you can use spectral techniques. But in this talk, we're going to take a different point of view. So you all know that a subset of 1 to n, you can capture the set by its characteristic vector, a vector that belongs to 0, 1 to the n. And that, of course, is just a matter of notation. There's nothing dramatic about that. But the nice thing is that 0, 1 to the n has a structure. We're going to think about it as a measure space. So if you pick a parameter p between 0 and 1, you can have a measure on 0, 1 to the n. So if you take any x and 0, 1 to the n, the measure of that vector is p to the number of 1s in the vector, p to the sum of xi times 1 minus p to the power of n minus some xi. So this is exactly the probability that if I flip n biased coins, I get the string of heads that I get is exactly the string I was looking at. And this is the measure of one vector. And if I have a family of vectors in 0, 1 to the n, then the measure of that family is just the sum of the sum over all x in the family of the measure of those vectors. So this gives us a measure on this space. And it happens to be a special measure. What's special about this measure? It's a product measure. And product measure is something very nice. Why is it nice? Well, whenever you have a measure space, you can look at functions on that space. In this case, you have a very nice basis for the family of functions, for the space of functions on the space. It's an orthonormal basis, and it's the Fourier basis. And this allows us to do Fourier analysis. And many people who are sitting here in the audience have written papers, have exploited this nice thing.
Now, do you mean orthonormal with respect to that measure?
With respect to the measure, yeah. So usually when you do Fourier analysis on 0, 1, then you do it with the uniform measure, which corresponds to p equals 1/2. But you can do the same thing for any p, and that's going to be important. Now, you're not going to see any Fourier analysis in this talk, but you will see some key ingredients that the only way I know how to prove them is using Fourier analysis. So if you look for the green star, that will say that that's something that I only know how to prove using Fourier analysis. Now, another nice thing about this, the measure space is that, so we have a parameter, this parameter p, and you can move p between 0 and 1, and somehow that gives you a different measure, and it enables you to focus on a different part of the cube. So, because of Chernov's inequality, most of the measure is concentrated around the n times p level of the cube. And somehow, when you say most vectors have a certain property, you can change your definition of most. And so this sort of reminds me of the difference between G and P and G and M, the random graphs. So typically in extremal set theory, you look at a family of sets of size k. But it's very useful to think of these sets of lying inside the cube as part of something continuous. And this is sort of reminiscent of what happens with graphs. So Erdős and Rényi defined G and M and G and P. I think of part of the recognition of how useful G and P is over the years. So for example, Erdős proved that you have graphs with arbitrarily large girth and arbitrarily large coloring number. So how does the proof start? It starts by varying the value of p. If you make p too large, you'll get a dense graph that has very small cycles. If you make p too small, you get a sparse graph that has small coloring number. So you have to choose the right value of p. Even then, you have to still make some alterations. But the possibility to say that most graphs under a certain definition of most have a certain property is a very powerful tool. Even though it enters the proof we'll see today in a very innocuous way, it's still very powerful. So the fact that we can shift around the cube. OK, so now I think we're done with philosophy, maybe we can move on to some mathematics. So here's the definition. What's an intersecting family? So we have some ground set. It's always 1 to n. An intersecting family is a family of subsets. Every two of them have non-empty intersection. And also, I'm not sure whether we'll use this definition or not. We can talk about cross-intersecting families. Two families where every set in A intersects every set in B. So let's start with an example of an intersecting family. Let's say I want to draw here on the board 10 sets, every two of which intersect. So that may seem like a formidable task, challenging combinatorially. Can someone give me a simple recipe how to draw 10 sets, which are pairwise intersecting? That's an excellent suggestion. I can draw a single point, and I can draw 10 sets, every two of which contain that point. OK, so that's a simple way of doing it. You could have offered me a slightly more sophisticated suggestion. So I chose 10 because 10 is 5. Choose 3. If you take 5 points and take all subsets of size 3, that'll be an intersecting family because you can't fit in two subsets of size 3 disjointly. But it seems that this suggestion, even though it's simpler, we can get much more mileage from this construction than from this one, in the sense that if I had 1,000,000 points and I say, now give me as many subsets of these 1,000,000 elements, as many subsets of size 3 as you can, such that every two intersect, well, I can't extend this example at all, but this one can be extended quite a lot. So it seems that this simple construction has potential to be the best construction. And of course, we'll see in a minute or two that it is the best construction. OK, we're going to talk about extremal set theory and Boolean functions. So now we've seen something that has to do with sets. Let's see something that has to do with functions. This is a definition probably most of you are familiar with. I have some function on the cube. It's a Boolean function. It only takes on values 0 and 1. And then what is the influence? So it depends on n variable. What's the influence of the ith variable? So I choose, here the probability is over x. I choose x at random in the cube. Yes?
This look and feel remarkably similar to differential cryptanalysis and the differential there. And this is
well, we'll see. This is a partial derivative of the function. Well, at least the L2 norm of the function that measures this influence is, in a sense, a partial derivative of the function. But anyway, back to the definition. You choose x at random according to this measure, and you look at x and x where you flip the ith bit. And you ask, does this change the value of the function? And the probability of that is the influence of the ith variable. So for example, let's take simple function, the majority function. So what is majority of x is just, it's 1 if most of the coordinates in x are 1. So it's 1 if sum xi is more than n over 2, and it's 0 if sum xi is less or equal to n over 2. And let's see what is the influence of the ith. This is a symmetric function, so for every I, you get the same influence. What's the influence of the ith variable on the majority function? So when does the value of the function change when you flip the ith bit? If the other bits were precisely balanced, then we know the probability of that is of order 1 over square root n. It's approximately 1 over square root 2 pi n. So it's of order 1 over square root n. And then if I sum up all the influences, so I'm going to denote that by I of f, the sum of all the influences, so it's n times square root 1 over square root n. So it's of order square root n. OK, so this function has the sum of the influences is square root n, which may seem pretty large. And actually, it is the largest possible. Now I want to look for a function that has a very small sum of influences. So of course, it's very easy to find a function where the sum of influences is 0. Which function is that? A constant function. There is no influence. But that's cheating. Let's try to look for a function whose average is 1/2. So I'm looking for a Boolean function which is 1 on half the cube and 0 on the other half of the cube. And so wanted dead or alive, such a function where the sum of the influences is only 1 rather than square root n. So I want a function where I sum over all the influences, I only get 1. So can anyone except Ryan and Guy and Irit and Asaf give me an example of? Sorry if I left. Very good. Okay. Pardon me? No. So that would violate KKL. Christian asked, can I find such an example where all variables have the same influence? That's impossible. But as other astute members of the audience have remarked, you can look at this function. F of x is x1, just depends on the first coordinate. This is called the dictatorship. And indeed, in this case, the first coordinate has influence 1. It always changes the value of the function. And all the rest of coordinates have influence 0. So this gives you what we wanted. Now, and it turns out, and we'll see this in a minute, that, well, I won't show you that this is precisely extremal, but this is an extremal example. And there's some philosophical connection between the two examples we just saw. The first example, I was looking for a large intersecting family, and the largest intersecting family, and that's a theorem that you'll see in the next slide, is the one you get by fixing one element and taking all sets containing that element. Here we're looking for a function that has a low sum of influences, and I'll give that a geometric interpretation in a minute. And the easiest way to get such a thing is to take a function which depends on only one coordinate. In that case, that minimizes the sum of the influences. So we see this recurring theme here. And so now I want to give you some, we've done definitions, we've done examples. It's time to move on to theorems. So let's see some genuine theorems. So the first theorem is, this is perhaps the fundamental theorem in extremal set theory. It's the Erdős-Corrado theorem. You take some parameter k, which is less than n over 2, and you want an intersecting family of k sets. What's the largest possible value size of that family? The largest possible is n minus 1, choose k minus 1. And the formula gives you the hint to what the extremal example is. It's a principal family. It's all sets containing a fixed element. So this is a theorem. OK, now I said we're going to move back and forth between sets and Boolean functions. Let's see. Now I want a theorem. This was a theorem about the kth level in the cube. Now I want a theorem about sets without a restriction on their size. I want a theorem about the whole cube. Well, the first analogy that comes to mind is really boring. If I just ask for any family of sets at intersecting, how large can it be? Well, it can't be more than half the sets in the cube, because you can never have a set and its complement. And there are many different ways in which you can take 2 to the n minus 1 different sets such that you get an intersecting family. So that seems sort of not interesting. And the reason it's not interesting is because it's not the right question. The right question isn't how large a family can you get, but what's the largest measure of such a family? Here you had the parameter k, and in the correct continuous question, you have a parameter p. So just like k was less than n over 2, here p is less than a half. And I take an intersecting family of vectors. So intersecting for vectors means that the sets of which these vectors are characteristic vectors are intersecting. Every 2 such vectors share a coordinate where they're both 1. If you take such a family, how large can it be according to the measure? The largest it can be, its largest measure is p. And once again, this can be achieved by a dictatorship. You take this function. This function is the characteristic function of the set. This is the largest possible intersecting family under that measure. OK, so these were 2 theorems about intersecting families.
So didn't you tell me before that if I require it to be symmetric, it would violate this theorem? So why would it violate it?
No, I didn't say it would violate it. I just, if you ask,
violate KKL theorem.
Oh, KKL.
no, it would. You asked about the sum of the influences. If I wanted the sum of the influences, we'll talk later about minimizing the sum of the influences. That was a totally different question.
So this is a new result, right?
This is well, I used to think it was new. I first came across it in Irit's thesis. She proved something with Muli stuff, or something a bit stronger than this. But then I discovered it's folklore. So I have one proof of this, but then when I published one of these proofs, I got tens of angry letters that I've proved this before. So there are many. I know by now about 7 different proofs of this theorem. So I don't even want to state whose it is. Just call it mu Descarado. Oh, and I forgot. This is the point where I should start accumulating the examples on the board, because we're going to be using all of them in the second half of the talk. So this is the first thing we're going to be using. So let me write here mu Descarado says that if A is intersecting, then the measure of A is less or equal to P. Okay, so this is shorthand, but I think it'll suffice to remind us of the theorem. Okay, so now I want to show you some more Occam theorems. One type of place where you expect to see Occam theorems are isoperimetric inequalities, because when you're trying to minimize, you're given a fixed volume and you're trying to minimize the boundary, it makes sense to try to do something as simple as possible. So I don't know, you may argue with me whether this is an Occam theorem or not, whether a circle is really the simplest possible geometric object, but of all planar sets of a given measure, the minimal perimeter is achieved by the disk. Okay, so we can argue whether a circle is really the simplest or not. Just like in applying Occam's Razor, you can argue whether intelligent design or evolution is a simpler explanation to the fact that we're sitting in this room. But anyhow, so okay, so the next I want to show you, the next theorem is also an isoperimetric theorem, and has to do with influences. So I just want to point out that influences also have to do with isoperimetry, because if this is the cube 0, 1 to the n, so this is supposed to denote the 0th level, 1st level, 2nd level, up to the nth level, and you have a subset of this cube, then and I look at its characteristic function, and then ask, when I flip the ith bit, does it change the value of the function? I'm really asking how many edges go between this set and its complement in the ith direction. And when I sum the value of the influences, I'm asking how many edges leave this set. And I weigh them according to a certain measure. So this is, in some sense, it's a measure of the boundary of the set. So I asked you, if I fix the expectation of the function, how small can I make the boundary? And the simple example we saw was where you take a function that depends on only one coordinate. So it was kind of, I was asking you for an isoperimetric problem, and you gave me a solution where you take something of low dimension, something one-dimensional. And of course, every time you take a function that depends only on 7 coordinates, the sum of the influences will be at most 7. And the question is does this also work in the other direction? Is it true that if I have any function that has a low sum of influences, a small boundary, does that mean that the function really depends on few coordinates? And the answer is more or less yes. So here's the green star that says that this is something I only know how to prove using Fourier. So if the sum of influences of f is bounded by some bound b, then indeed f is close to a function which depends on few coordinates. So it's close to some function g, which is also a Boolean function and depends on few coordinates, where few, what I mean by few, well, it depends on what the bound was and how good an approximation you wanted. Okay, so let's, by close, I mean an L2 approximation. Let's just write this theorem here, that it small sum, well, let's say if the sum of influences is bounded, then f is epsilon close to some junta. So if you've never heard this terminology before, a function that depends on one coordinate is a dictatorship. A function which depends on few coordinates, if you come from South America, it's a junta. So this tells you that juntas have this isoperimetric property. And now so this was isoperimetry on a certain graph. The next Occam theorem that we're going to use is a more classical set theoretic theorem, and it's also something about a graph on the cube. Now the question is a bit different. It starts, as most classical extremal set theorems start, on the kth level and ask you to take a bunch of sets of size k. So let's call this AK. This means the kth level of some family A. And now I'm going to look at the upset generated by them. I'm going to look at all k plus 1 sets that contain one of these sets, and then at all k plus 2 sets that contain one of these sets. I'm going to go up to some level L larger than k and look at all sets that contain one of the sets in my family. Let's denote that by AL. And the isoparametric question is, I tell you the size of AK, and you try to minimize the upper shadow, AL. Okay? So there's a theorem that tells you the precise answer for that for every single size you can think of AK. So we won't use the most general statement of the theorem. We're going to use a special case of that theorem. So this is the Kruskal-Katona theorem. Let's say, let me write it here on the board. Kruskal-Katona. Let's say that the size of my family on the kth level is at least n minus r, choose k minus r. So r is some parameter. It can be 1, 2, 3, whatever you want. And I'm trying to minimize the upper shadow. Then what this tells me is that on the nth level, the size of my family is at least n minus r, choose L minus r. Now once again, the statement of the theorem, the formula in the theorem gives you a clue to what the extremal example is. Out of all the n choose k sets, I'm allowed to choose n minus r, choose k minus r. What does that number remind you of? You fix r elements, and you choose all k sets that contain those r elements. So this gives you n minus r, choose k minus r sets. If that's the number of sets you're allowed to choose, then that is the best choice. That gives you the minimal upper shadow. If that's what you do, you take all sets that contain r fixed points, then on the nth level, the upper shadow is going to be the same thing again. It's going to be all sets containing r fixed points, and this is going to be the upper shadow. Okay, so this is a similar type of theorem. Okay, so now we're more or less done with the examples that we're going to use as lemmas. And I want to show you just one more pair of theorems that are sort of a theorem about the whole cube and a theorem about one level in the cube. And the reason I want to show you these two theorems, there are two reasons. One is because I think it gives you a nice example of what you can get by moving back and forth between the two perspectives. And the second is it'll give you some, or this is the historical motivation for us to work on the theorem I'm going to show you today. So the theorem I'll show you today sort of follows naturally from these theorems in the sense that it's a natural question to ask. So here's a GNP-ish theorem. This is the theorem on the whole cube. So fix some parameter p, and I want to bound it away from 0 and 1/2. So let's say it's between beta and a half minus beta. And now you take some intersecting family. So we already saw before that the largest measure this family can have is p. Now, it's also true that this is unique. This is the unique extremal example. The only way to achieve that measure p is by taking a dictatorship. That's the only family that has that measure. And the new part, so this is something I talked about last year in Microsoft. I'm sure you all remember my talk from last year, except for Uri and Sefi, who weren't here last year. But so the robustness, and this is the green star, meaning that the only way I know how to prove this is using analysis. What happens if you're close to the optimal size? So what can you say if your measure is p minus epsilon? So if I force you to be maximal size, there's only one structure which is possible. It turns out that even if I give you a bit of slack, you can't change much. If the measure of the family is p minus epsilon, still you're close to the optimal structure. You're close to a dictatorship, close up to a constant times epsilon, where the constant depends on beta. Okay, so this is a theorem about the cube. Is the theorem clear?
What does it mean for a set to be close So dictatorship.
So you have a set which is a dictatorship or a half cube, and the measure of their symmetric difference is constant times epsilon.
In the measure mu.
Yeah, for the measure mu p. Okay. Now, so this is the theorem about the whole cube. Now here's the corollary that you get on the kth level. So before p was between beta and half minus beta, now k has to be bounded away from a constant and from half n. So k over n is between beta and half minus beta. And now you go back to the classical Erdős-Corrado setting. You have an intersecting family on the kth level. And it's close to, the largest you can get was n minus 1, choose k minus 1. And this family is close to the maximal size. Then the corollary from what we saw before, and I'm not saying how it follows, is that it's close to the optimal structure. So if you're this large, then you have an element that belongs to almost all the sets in your family, where almost all means all but a constant times epsilon times the size of the family.
This one doesn't have green star, so you can prove it without...
Well, I can prove it as a corollary from the slide, the theorem on the previous slide, which had a green star. So I could add a green star here. No, green star means directly from. Okay, so and you can prove similar theorems if you want a 2 intersecting family or a 3 intersecting family. I won't go into that now. Okay, so we finished with the philosophy part and the examples part, and now I want to reach the main theorem I wanted to talk about today. And this theorem is going to hold for any value of k, but the interesting range of k's is going to be where k is little o of n, but goes to infinity. Actually, maybe it's interesting for any k, just little o of n. And you'll see in a second it's important to get the scaling right. In this range of k's, n choose k is much, much larger than n minus 1 choose k minus 1. The ratio between these two things is k over n. And this is much, much larger than n minus 2 choose k minus 2. So, but this is the same as n choose k minus 1. So the dramatic change in size happens when I change the downstairs parameter. And what this means is that this is a bad marker. If this is my cube, and this is the kth level, so I'm not drawing it on scale. If I drew it on scale, it's little of n. It would have to be down here. The size of this whole thing is n choose k. And if I have an intersecting family, it's going to be already much, much smaller. I can only take a minuscule proportion of all the sets. It's going to be of size n minus 1 choose k minus 1. And I'm going to prove a theorem where the error is of this size. So the error is going to be minuscule compared to the size of the maximal intersecting family. Now, if you remember, here we saw that if you're close to the maximal size, then you're close to the optimal structure. Now I'm going to give you much more slack. I'm saying you don't have to be close to the optimal size. I allow you to be 1% of the optimal size. You know what? I allow you to be 1/1,000,000th of the optimal size. Can you then do something totally different? So well, if you don't want to be special and different, there's something very simple you can do. Take a maximal intersecting family and take 1/1,000,000th of the sets there at random. That gives you an intersecting family which is of size 1/1,000,000th. Now the question is, can you do something different? And to me, it came as somewhat of a surprise. No. So essentially, and the key word here is essentially, we'll have to understand what that means. There is nothing else you can do. The only intersecting families are subfamilies of a principal family. And by essentially, I mean, you draw me some intersecting family, I'll be able to capture it inside the principal family. But of course, I'll be missing some little, how do you say chupchik in English? Some little blemish that will not be captured by the family. But the size of this blemish is going to be of order n minus 2, choose k minus 2. Here, yeah, that would be quite useful. So here's the theorem. The theorem says that all intersecting families are essentially contained in a principal family. So let AK, it's a family of K sets, it's an intersecting family, then there exists some principal family B such that A is almost contained in B. After I chop off B, I'm left with anything that's not in B. It's only of order n choose k minus 2. Because now you see why this theorem, it's not that interesting for large k, because for large k, n choose k minus 2 is the same as n choose k. So there it's saying something really trivial. But when k is small, it says something which may be a bit more surprising. Now, this theorem is the best you can hope for. Why is it the best you can hope for? Well, so let's try to build an intersecting family which isn't a principal family. So instead of saying all sets containing a fixed element, let's fix 3 elements and look at all k sets which contain at least 2 out of these 3 elements. So that will be intersecting, right? You choose 2 and I choose 2 will have to intersect. And there it's sort of hard to capture all this family in an intersecting family. If I decide to take all sets that contain this element, then how many k sets am I going to be missing? I'm going to be missing all k sets where I choose the other k minus 2 elements from here. So it's going to be n minus 3 choose k minus 2. So I'm going to be missing order of n choose k minus 2. So this is a family that no matter how you try to capture it with the principal family, you're going to be missing this many sets, which isn't surprising. This is the size of the whole family. So this theorem is tight. You can't improve it in that sense. But this, from an Occam point of view, this isn't so pessimistic. I was trying to give the simplest possible explanation, show that you can be contained in a principal family. Well, here you have a pretty simple explanation. It doesn't depend on 1 element. It depends on 3 elements. So if you allow me, if I want to give a more complete explanation, here I can once again give a simple explanation. And if you allow me to move from 1 to 3, then my error term will become even smaller. So here's the continuation of the theorem. This principle holds on a finer scale. If you allow me to give an explanation of size 2r minus 3, then the error becomes really small. It becomes order of n choose k minus r. Remember, each time we enlarge r by 1, this error drops dramatically. And once again, this is tight. The same sort of example shows that you can't hope for anything better than this. So what I want to do in the last, oops.
Less than, not at most, because then it doesn't work for r equals 1.
Pardon
R
me?
equals 2.
If r equals,
No, r equals 2.
R equals 2 is this case, yeah. So, okay, so now I want to spend the last 40% of the talk, that was a joke, proving this theorem. So I won't give you all the details, but I want to give you a sketch of how to prove it. So this is what we want to prove. We're starting on the kth level. We have a family of k is little o of n. We have a family of intersecting k sets, and I want to show that I can capture it in a principal family up to this error factor. Okay, so I put up some lemmas there that I'm going to use, and there's one final lemma that we should use, and this is Russos lemma. So let's read what Russos lemma says. I have a monotone subset of the cube, and f is its characteristic function. Then if I look at the measure of the set and look at its derivative, this is exactly the sum of the influences. So that's sort of mysterious. Let's take a look at it. If I have a monotone set, then the larger p is, the more likely I am to fall into the set. It's a set where if I change from 0, any coordinate from 0 to 1, I can only enter the set. So when I'm flipping my coins and I make them more likely to become heads, the probability of ending up in the set is larger. So if I draw the measure of the set as a function of p, then it's increasing. It's an increasing function. It increases from 0 to 1. And we're going to be interested, what is the derivative at a certain point? So I think of this as a function of p. And what's its derivative with respect to p? It turns out that its derivative is exactly, I look at the characteristic function of a, it's exactly the sum of the influences. This is a sort of mysterious formula, which also shows you something about the importance of influences. We're not going to prove this formula. Let's just take it for granted. Although this is a really simple lemma. It has a 2-line proof, but I won't show it. So Russos Lemma says that the sum of the influences is equal to the slope of this function. This isn't the partial derivative. It's just my bad handwriting. Remember when Joel was visiting Jerusalem, he complained that I don't know how to write a D. So I haven't improved since then. OK, so now let's look at the proof. So let me show you all the steps, and then we'll go through them one by one. OK, so let's draw our cube again. So here's our cube, and we're starting on the kth level. And we have some sets on the kth level. So the first thing we do is we consider the upset generated by those sets. We want to work in the whole cube where we can do some analysis. So one level is too restrictive. We sort of turn the thin problem into a thick problem. We get a subset of the cube. OK, now we want to say somehow that this subset is very simple. We'd like to say that this subset is a junta. Well, whether it's a junta or not will depend on our perspective. So we'll find a perspective for which this family is a junta. And then this is going to be too easy. We're going to see that it's trivial to find a perspective in which it's a junta, so we have to be careful. It's not too easy. We have to show that this junta is non-trivial. So trivial junta is a junta that depends on 0 coordinates. It's a constant function. OK, so we're going to show it's non-trivial. And now, once we've shown that this is close to a junta, so let's say the junta depends on 3 coordinates. OK, so junta is a function that depends, let's say, on the first 3 coordinates. So these 3 coordinates, I better use a new color here. Where's the black marker? I like the black marker. Disappeared. Oh, here it is. So this junta divides the cube into slabs, divides it into 8 slabs. What is this slab? This slab is all vectors that start with 0, 0, 0. So it's 0, 0, 0 cross 0, 1 to the n minus 3. What is this slab? This is 1, 0, 0 times 0, 1 to the n minus 3. And this is going to be 0, 1, 0 times. And let's just add one more. This last one is 1, 1, 1. So I can divide all vectors according to what happens in the first 3 coordinates. And now, per Irit's request, we're going to zoom in on what's happening on the kth level. We've just divided the kth level into 8 parts. This is 8, even though it doesn't look like 8. And so and now we have to take care of these parts. So first, what we really want to say is that almost all the sets in our family sit in a part like this, all vectors which start with 1, 0, 0, for example. So first of all, we'll have to get rid of this part. Show that we don't have too many vectors in our family that have 0, 0, 0 in the first coordinate. Then we're going to get rid of these parts, the parts 1, 1, 1, 1, 1, 0, 1, 0, 1, 0, 1, 1, all parts which have more than 2 1s. And then we're going to be left with the contenders. We're going to be left with 3 slabs, which could be, one second, Gideon, I'll answer you in a sec, which could be a dictatorship. So these are wannabes. They're vying for the title of dictatorship. And I want to show that only one of them, that you can't have two of them simultaneously. Doing this, that if I look at my family, I can have a lot of sets here and I can have a lot of sets here, but not simultaneously. There's only one such slab where all my family is sitting, and then we're done. OK, so you had a question.
Shouldn't it say more than one coordinate or two coordinates or more? What line 5
Oh,
you said.
I meant at least. I meant greater or equal to, and I wrote greater. Thank you. So at least two coordinates. OK, so is the plan of the proof clear? OK, so now let's see how we do this. So step A is pretty clear. Now we have to look at step 2. So I want to find a perspective for which A is approximately a junta. So this is going to be a very easy part of the talk because we only have a limited number of tools. So it's like in the difference between an exam and a course and an open exam at the end of your undergraduate studies. When you have a problem and you know that you have to use calculus to solve it, it's easier than. So here you have only a limited number of tools. I want to show that something is approximately a junta. Which of these tools do you propose I use? Well, this is the only one that says when something is approximately a junta. It's a junta when the sum of the influences are bounded. OK, but what do I know about the sum of the influences? Let's see. Does any of these say anything? OK. So I'm looking. To show that the sum of influences are bounded, I have to show that the derivative of the corresponding plot is bounded. So let's draw this picture again. We have the measure of A as a function of P, and we have P going from 0 to 1. And here it is. And let's focus our attention on one interval, let's say between a quarter and a half. This is just an example. And I would say that somewhere here the slope is bounded. Well, of course, somewhere here the slope is bounded. This is an interval of length 1/4. Slope can't be larger than 4 all throughout this interval. Otherwise, it would shoot out the top of the picture, right? So there exists some P somewhere in between 1/4 and 1/2. And if I fix that P as my perspective, this looks like a junta. Okay, now this is a ridiculously simple trick. It sounds too simple. Sounds like there's something fishy here. So this trick, I think, so there's a paper called The Importance of Being Biased. And the name of that paper comes from this trick. So it's Muli and Irit's paper. It was Irit's thesis where they first used this trick. And what this argument shows is that any set is a junta for some P. But if any set is a junta, it sounds almost like an empty statement. So for example, if I look at majority, majority is a function which depends on all coordinates simultaneously. How can it be that majority is a junta? So if I look at this, try to do this proof for majority, this is what the plot for majority looks like. It's very sensitive to the bias of the coin. If the bias is slightly above half or slightly below half, then the function is almost determined. So right here, for p equals 0.49, it's true that majority is a junta in the empty sense. It's just a constant function, so it depends on 0 coordinates. So now it's true that every function is a junta somewhere, but the point is to show that it's a non-trivial junta. So we have to show that at this point, it doesn't look, we're not here and we're not here. We're not very close to 0 and we're not very close to 1. Okay, and then if we're bounded away from 0 and 1, then we know that we're a non-trivial junta. So next step is to show we're bounded away from 1. So we need some upper bound on the measure of the family. So once again, since we have so few tools on the blackboard, it's not going to be hard to decide which one to use. I'm going to use this tool. A is an intersecting family. Remember, we started on the kth level. All sets were intersecting. So also the upset generated by them is an intersecting family. For any p less than 1/2, the measure of the family is less than p. So if we go back to this plot, it's sitting beneath this plot. So it can't be 1. So we ruled out this situation. How about the other situation? Maybe it's very close to 0. Well, if we started out with a family A, which was of size less than n minus 2, choose k minus 2, then we're done, because that was the degree of approximation I wanted. So if my family is so small, then the theorem holds automatically. So we can assume my family is large. It's larger than n minus 2, choose k minus 2. Well, if on the kth level it's larger than n minus 2, choose k minus 2, looking back at the tools on the board, we know that on the lth level it's going to be larger than n minus 2, choose l minus 2. So when I go up to the levels somewhere between 1/4 and 1/2, here my family is quite thick. It's larger than n minus 2, choose l minus 2. Way down here, this was really a minuscule proportion. But when I come up to here, n minus 2, choose l minus 2, divided by n, choose l, this is approximately l over n squared. So here it's something at least 1/16. When I come up to, when l is a constant times n, this is a constant proportion of the layer. So the moral is, when I look at the upset, in these levels of the cube, it fills in a non-negligible proportion. And when I decide to use this measure, I'm focusing on this part of the cube because of Chernoff. All the measure is here. So most of my family, where most of the measure of the cube is, my family is at least 1/16. So it's not close to 0. So we showed it's a non-trivial junta. It's not close to 1. It's not close to 0. OK, so now we're in business. Now we know that family looks more or less like a junta. So I didn't give you the exact quantitative statement, but I can give a bound on the size of the junta. In my example, it was 3, but maybe it's going to be 1 million. I'm not going to care. I can divide the cube into 2 to 1 million parts, and now go on to the next steps in the proof. And I know that my family, when I look at the cube from this perspective, most of these slabs, either my family fills almost all the slab, or it fills almost none of the slab, for most of them, because this is a very good approximation of my family. So now I know what's happening in the rest of the cube. I can project down back to the kth level and try to prove something there. So let's skip this for a second. This is perhaps the hardest step. I have to discard the empty assignment. Let's talk about the heavy assignments. So heavy means all assignments where I have at least 2 1s or 3 1s. But there aren't very many such. The size of each slab here on the kth level is very small. The size of this slab is of order n minus 3, choose k minus 2, because I've already used up 2 of my k1s. So this is already of the order of magnitude of the error that I allow myself. This whole part is small enough that I can neglect it. Now here, crucially, I'm using the fact that I have a junta. I have only 2 to the power of 1 million parts. I have a constant number of parts. So if I have a constant number of parts and they're all small, then I can forget about all these parts. Of course, if I didn't know it was a junta, each such part would be small, but I've had a huge number of such parts, so I couldn't cancel it out. So here I'm using the fact that it's a junta, so I can get rid of the heavy parts. And let's assume for a second that I also got rid of the empty part. I think I'm not going to tell you how to do this. You're getting tired. It's close to the end of the talk. So now we come to the place where I have to show that at most one dictator is substantial. I want to show you that I can't have I can't have much more than n minus 2, choose k minus 2 sets in my family that start with 1, 0, 0. And I can't have much more than this number of sets which start with 0, 1, 0. So I want to say I can't have many sets here and simultaneously many sets here. So look, any vector that starts with 0, 1, 0 and 1, 0, 0, and they belong to my family, they're supposed to intersect. But the intersection doesn't happen in the first 3 coordinates. So if I forget the first 3 coordinates, what do I have? I have a cross-intersecting family. If I forget about the first 3 coordinates, every vector here intersects every vector here. Now, there is some theorem which is quite similar to the Descarado theorem, which tells you something about cross-intersecting families. So I didn't want to load too much information on you, so I'm not going to tell you the theorem, but it's sort of an Occam type of theorem saying that you can't make both, if you have a cross-intersecting family, you can't make both this large and this large. One of them is going to be small. So the conclusion is going to be that I can't have two dictatorships where both of them capture a lot of sets in my family. So I cross everything out, and I've proven my theorem. The only part of the layer where I can have a substantial part of my family is one slab which corresponds to one dictatorship. So I've shown that my family is contained in a dictatorship. So, and that concludes the proof. Now, so are there any questions about this part of the proof? No question. Okay, so the next thing is what would have happened if I wanted to get a better degree of accuracy. So remember, I promised you that I can show that if I want, let's say, n choose k minus 10, then I can show you that it's contained in a family that depends on at most 21 elements or 17 elements. So the proof would look pretty similar, but now the end of the proof would be much more complicated. When I look at two dictatorships, I could show that I couldn't have more than n minus 2 choose k minus 2 vectors here and more than n minus 2 choose k minus 2 here. But if instead of k minus 2, I'd write here k minus 10, then I couldn't be finished yet. It may be the case that I have many more than n minus 2 choose k minus 10 here and more than n minus 2 choose k minus 10 here. So I need something stronger to push this theorem through. And what you have to use is induction. So you need induction. And as usual, when you do induction, it's easier to prove a stronger theorem. So you saw here a cross-intersection comes into play. So the stronger theorem that you have to prove in order to be able to use induction is some theorem about cross-intersecting families. But we're not going to go into that now. And OK, so now let me summarize. So first of all, I showed you some simple statements. So I wrote in the abstract, I consider some of these to be fundamental theorems in extremal set theory. I mean, this is more or less the simplest question you can ask. Is it true that every intersecting family is, you have a very simple, it's an intersecting family because it's contained in a junta. So there are a lot of similar questions that are still open. This is sort of work in progress. We haven't written the paper I just talked about yet, because some of it is also conjectures that we have an idea how to prove, but we haven't proven yet. So this is still, this hasn't, we haven't said the last word yet about these type of theorems. So one message, which is, I guess, a very clear message in this talk, that it's useful to look at the set theoretic questions embedded in 0, 1 to the n. And one very vague thought that I've had, that I don't know if it's nonsense or not, it might be beneficial to merge this approach with the homological approach. So Ron Aharoni, Eli Berger, Gil Kalai, Roy Meshulam, all these people have visited Microsoft lately. They've proven some very nice theorems about the independence simplicial complex of a graph and vector representations of graphs. And they use algebraic topology. And when I look at their theorems, I smell a very similar spirit behind them. And somehow I have a feeling that putting these two approaches together could yield some interesting results. But that's just a very vague thought. I don't have anything to back that claim. And that's it.
How do you get rid of the sparse sets?
Oh, these sets. Well, OK, so this family is a monotone family, right? If any vector, we're looking at the upset. So if any vector belongs to it, everything that's above it also belongs to it. Therefore, if any vector here belongs to the set, its brother here will also belong to the set, etc. So if I look at the density in this slab, it's going to be less than the density in this slab, and less than the density in this slab, et cetera, et cetera. Now, if I had this many sets here, it would mean that the density in this slab would be large because of this Kruskal-Katona argument. So I'd have a lot of my family sitting in this slab, but then I'd have a lot of my family sitting in every one of the slabs, and that would contradict the notion that in some of the slabs it should be 1 and some it should be 0. So that would show that. So that's the argument, basically.
So that's called Kal vachomer.
Yeah, I don't know. I never know how to say Kal vachomer in English, let alone
A fortiori.
Yeah, it's some Talmudic line of reasoning, but I don't think it has a name in English.
English.
Okay, thanks.